Today's focus is on sampling design and statistical analyses. So first I just wanted to sort of start out by saying in environmental science and ecology, we basically have a really tough job. The world is really messy. So here's an example of a nursery. It's like, okay, all of our plants are in nice rows. They're evenly spaced. That'd be probably a pretty easy place to sample information. But even within this nursery, what if you were interested in differences in flower color? Well, even within this nursery, which is nicely, evenly spread out, we've got plants of slightly different sizes. We've got plants that have different colored flowers, even within the same bush. So the world is kind of a messy place, and how do we design sampling protocols to deal with that, to be able to sort of extract the signal from the noise? And so here's another example. So this is local rainfall in the Ventura River watershed, and we've got the Ventura, Ojai, and Medillaha Canyon rainfall gauges. Those are all pretty close, right, in space, but we get a lot more rain in Medillaha Canyon than we do in Ventura. And so thinking about space, time, all those things can really affect how you're sampling, where you're sampling, how do you distribute your samples in space and time. So just thinking about the world is a messy place and how do we deal with that. So contrasting our nursery with a more natural system. We've got a number of different species present here. They're not evenly spaced in our habitat. How would we analyze or collect vegetation information or vertebrate information in this context versus in this context? So I'm going to talk a little bit about some of the different techniques that scientists have come up with. But first, I want to sort of walk you through the scientific process. And I think one of the most key aspects of the scientific process is defining your question or your problem. I suspect at some point you guys have experienced, you have a method and you're really excited about it. Maybe it's drones, maybe it's underwater vehicles, maybe it's something else. You've got a method, but you don't have a question. And without a question, you're sort of just wandering about. And some of the papers you guys are going to read later on in terms of like long-term monitoring are some of the struggles like not just you have faced. Scientists have tried to do these sorts of things for years and years, and when you don't have sort of a fundamental question or problem you're trying to address, you're just going out and collecting information, it may be valuable, but it may not answer the question that you wanted. And so if you have a particular question and you're not just a naturalist, defining things is really important. It seems maybe intuitive that the next step would be, well, define what are you going to study? Like what plants are you interested in, or what animals are you interested in, or what community or ecosystem dynamics are you interested in? Your next step from having defined the question and what you're going to study is to design your experiment or your survey. And we're going to spend a fair bit of time thinking about experimental design. Some of the questions you're going to get on the reading are how would you design an experiment if you wanted to answer this question? From that, selecting a sampling procedure. And when I say sampling procedure, I don't just mean sort of the mechanistic, you're going to go out and you're going to grab a sample, but thinking about the statistical ramifications of the sampling procedure that you're having, and we'll talk about that in the second half of lecture today. And then how are you going to obtain a representative sample? And when I say a representative sample, I'm really meaning something that is not sort of the outliers of your population. So if we had some of the plant examples I had earlier, thinking about are you grabbing things that are in the norm or things that are well outside the norm? So let's see here. So then you're going to actually start implementing your study. So you're going to be observing and measuring your samples. And then, again, something that maybe seems intuitive, but it's really easy to get out of, is to analyze your data objectively. It's really easy to go into a project or go into some question thinking you already know the answer. And some of the reading I think Carbon talks about it is trying to force a particular hypothesis on a system where it's maybe not appropriate. And so it's really important to step back, and sometimes you have to force yourself to step back, even in an experiment, or maybe you make it a blind experiment. So somebody sets up your treatments, but you don't know what the treatment is until you actually have done the data analysis here. You know their groups are particular groups, but you don't know why they're getting the treatment they're getting. And so being able to analyze your data objectively and think about what are the patterns that I'm seeing and not the pattern I want to see. And then interpreting your data and drawing conclusions from it. So that goes back to your analyzing your data objectively, and were you able to perform appropriate statistical or hypothesis tests that allow you to actually draw a conclusion? Maybe you weren't. Maybe, like, one of the things that Carbon talks about is, hey, a lot of things fail. A lot of field experiments don't work the first time. I think he says something like, if you get maybe 2 out of 7, you're doing awesome. So don't be afraid of failure. Don't aim for failure, but realize that things don't always work the way you anticipate, and sometimes you need to maybe adjust your question or adjust your approach to actually get an answer to the question you're looking for. And then the all-important reporting your findings. And I think I have a lecture at the end where we're going to talk about like how do you make something compelling? How do you tell a story? Sometimes it's interesting, we say maybe you're giving a presentation, for somebody to hear the history of how you got from point A to point B. But a lot of times that history sort of obscures the findings that you have. And so thinking about, well, what did I do? What are the findings I have? And what are the conclusions from those findings? So thinking about it in that sort of framework. All right, so I think a great resource for this is your textbook on asking good questions. What are good questions? How do you approach a good question? And one of the things that I have seen very dramatically as a professional in environmental science is people don't often ask the questions that give them the answer they're looking for. And really thinking about, okay, so for example, we have a water release plan for our dam. Some of our regulators are like, well, you should answer this question that's about grazing. It's like, well, grazing has nothing to do with water releases. Why would I expect there to be some connection there? And so making sure that the question you're asking will get you to the answer that you're looking for. And within the limitations of the studies that you're going to have. Like, you probably don't want to try and do a small-scale study here that's looking at climate change in Iceland. Probably not going to answer that question. So just think about the sort of limitations. Okay. So back to our field notebooks. I've been doing environmental science for like 15 years now. I can still learn, and putting together this class was a great example for me to be looking back at my field notebooks and be like, well, how could I have made that better? And here's a couple of guidelines for things that are, I think, the key pieces of information you absolutely need to have in your field notebook. It's great to number your pages. So say a page gets torn out or you photocopy it. Having the page number, the year, and maybe your name on it will allow you to identify that thing in the future. Or maybe you leave Channel Islands and you leave your field notebook behind and somebody wants to go and do that same study. They've got your field notebook that says who did it, when did they do it, and it'll give them a little bit more information that would allow them to do a better study. It's really great to date every entry. It's also great often to put the time of day. You maybe won't need that particular piece of information depending on what your study is, but sometimes it'll give you a clue when you forgot to write something down. Well, I went out at 2 that day, and I remember going out in the afternoon that day. So, okay, maybe I can recreate, well, I did do that activity on that particular day, not on some other day because I went out in the morning on the other day. We'll talk a little bit about other reasons the time of day can be important. You obviously will probably want to know where you did your study, whether it be a GPS location or a place name. Sometimes it can be for yourself. If you think there's any chance that somebody else might want to use your field notebook, having something that's not just in your head is a good thing to have in your field notebook. It's often great to have information about the weather or some other condition of interest, whether, say, you're doing like a wildlife survey, the visibility of that day, or if it was really windy that day. Those would be good pieces of information to have when you're going back and you're looking at your data. It's not something that's on your data sheet or something that's required part of your survey, but when you're looking at your data, you're like, oh, okay, I couldn't hear anything that day. It was really dusty, so maybe I wasn't able to see the animals as well as I wanted to. I feel like I have to suggest this because we're in the CSU system. There was a guy, Grinnell, at the Museum of Vertebrate Zoology at UC Berkeley, who has this sort of framework for doing field notebooks. It's a little bit more intense than I choose to do, but it's a great example. And I'd suggest looking it up on the internet because it's got different ways that you could approach field notebooks and splitting out different components into different books that maybe is something of use to you depending on where you go with your career. Okay, so some other practical considerations. Data sheets. Data sheet design is an art and not a science. These absolutely in no way replace a field notebook. It's great to have data sheets. It's great to have something standardized so you could hand out to a colleague that's going to go and help you with a survey or something. You want it to have all the information on it, but your field notebook's a place for you to be able to describe in sort of more casual detail other things that don't fit into the constraints of your data sheet. I do want to emphasize that data sheets don't have to look exactly like the data entry side of things, and I think I'll talk a little bit more about that later. We will talk about standard operating procedures on Thursday, but suffice to say that for some types of studies, there may already be some standard procedure that you could use, and it's worth looking around and seeing if there is something and whether you need to modify it or if you can just go and use it straight up. Regardless of whether there's a standard operating procedure, writing up a protocol and an equipment list is crucial because everybody is forgetful, and you will absolutely go out in the field without some critical piece of equipment that you need. And if you have a protocol and equipment list, you can read through it quickly before you go out. And you can say, hey, these are the things that I need. You can go through your checklist and make sure you've got everything. One thing that I think is often ignored, and I know that I'm a mess with it, is thinking about how do you, like, even in this class, we may generate a ton of data. How do you organize that? How do you back it up? How do you make sure that you can use it and you can find the pieces of information out of it that you need? Think about it really critically. I don't have necessarily an awesome suggestion for how to best do it, but think about it. Really conceive of, well, how do I want to organize things before you do it? Because when you try and do it in the midst of things, it gets really messy. One thing that's particularly crucial as we're thinking as environmental scientists, but even as ecologists, budgeting. Like, you gotta have money to do a lot of these activities. You know, maybe you can find volunteers to help you, but volunteers have their own issues. And thinking about, well, how much time is it gonna take me to do something? Do I have the money or the people to do it? So maybe you have a really simple task, but it requires 5 people to do it. And they don't maybe even need any training, but if you need 5 people, that's a big logistical thing to organize, just getting those people together at the same time, even if they're doing it for free. So thinking about budgeting from a holistic perspective. Okay, so before I get into the sort of details on sampling, I wanted to have a little bit of a discussion about, do you guys have any ideas on things that we could do to make our field data comparable and meaningful? Something that, you collect some information here and somebody else collects some information here. How could we put those pieces of information together and be able to make conclusions? What sorts of things would you want to do?
Use similar vocabulary.
Yeah, similar vocabulary is important. Any other sorts of things?
Have like a universal data sheet that you use for every site that has the same categories.
That could be good if you were, say, designing your studies at the same time, or you were doing your studies at the same time, or you're all working together. I think that's a really critical component, is making sure you have some sort of standardization. But think about it maybe even more basically. What's sort of going to be your fundamental units that you're going to be able to compare? Can you think of anything?
Fundamental units, you mean like metric versus?
No,
I mean, like,
when
we can compare precipitation in two different areas, or we can compare species, or are we like two different studies? How can they compare and relate? Or like, I'm doing a study, I'm trying to answer a question, and I'm researching it in two different places.
all of those things. So
whatever data that's in another study, is you have to just try and find out whether or not it answers your question, if it relates to your question. Because if you're trying to find out about climate change in Iceland, and I did a study on lizards in the mountains here, they probably would compare and relate and be very meaningful to each other.
Mm-hmm. So think about it. Okay, here's an example. I drove a backcountry road this morning, and I saw 20 deer. Okay. What information might you want to know in addition to I saw 20 deer? Like, is there anything that if you were going to go out and look for deer, how would you compare that?
Where were they? What were they doing? Were they all grown-ups? Were they young?
What type of terrain? Was it in a canyon, or are you in a chaparral, or?
Yeah, those are really important things. Are there any sort of other numerical things you might want to know? So some specific location, yeah.
Number of species you saw?
That'd be important. But how would that necessarily, like, assuming we all have the same species concept, how would that necessarily help us compare information? You think of anything? So the only information I gave you was that I drove some road and I saw 20 deer.
You gotta know location, you gotta know that's
Okay. Think even more fundamentally. If I wanted to compare, so you're going to go out and drive some road. You saw 15 deer. How would we compare those numbers?
That road to another.
Yeah.
Over how long the stretch of the drive?
There you go.
Yeah.
So you need some sort of standardization. And what we're going to talk about in all of our field method techniques is really like standardization on some level. It's thinking about what are the sort of components that you need to be able to compare this piece of information to this piece of information. So if I were going to go and drive a road, maybe it would be good to know the speed at which I drove, the length that I drove, the time of day that I drove, and then you go and do that same information, and we could come up with deer per hour, deer per mile, and then you'd have a number you could compare. But without those other pieces of information, it's just a number. It doesn't have any sort of context. And so thinking about those sorts of things is really fundamental to basic field methods. So I want to give you a couple of examples of basically ways that people have come up with for standardizing things. And I want to sort of stress that none of these techniques are, maybe not none, they're not necessarily mutually exclusive. So when I talk about plot sampling, you might combine plot sampling with another technique because they both are going to provide you with different sort of components. So plots is kind of the most basic idea in field methods. And it's really just a manageable area of some known size that you're going to use for sampling. One thing that you guys are going to have access to today and throughout the rest of the class are quadrats. And a quadrat is really just a fancy way of saying a square little plot. And you can make a quadrat of any size that you're interested in. You generally want to size them for the particular thing that you're interested in, and sometimes it'd be appropriate to have a really big quadrat, and sometimes it'd be appropriate to have a really small quadrat, and it really just depends on what you're looking at. And so here's an example of somebody going out and doing a quadrat measurement, and she's actually doing a quadrat within a quadrat. So you can see in her hands she's got a smaller quadrat that she's got within her larger quadrat. And one thing that I wanted to emphasize, and we'll talk probably too much detail in the statistics section, is thinking about, well, how many replicates do you need to have something that's representative? So if we're studying deer, using that same example, probably a quadrat that's this big wouldn't be great. You could have maybe a much larger, maybe a kilometer by a kilometer quadrat that you could use. But how would you space those through time, or space those through space and through time, that you could have the information that you're looking for? But basically, the idea is you're going to be able to relate some metric to an area. And that's almost always something that people are interested in. It's like density is something that people are always asking about. Populations, like you kind of need, like, if I give you 20 deer, again, it matters, well, how big of an area. If we had 20 deer in this classroom, that's a ton of deer. But if we had 20 deer, over Ventura County, that's not that many deer. So thinking about area as one of the components that we're interested in. All right, so things that you can get out of plot sampling. A lot of this is coming directly out of your Brower textbook. Again, this is a really great resource for just sort of the basic concepts in sampling design. And so these are some of the definitions that I want you guys to be thinking about. So density is really just individuals per unit area. Relative species density is when we're thinking about the number of individuals in a given group as a proportion of all the individuals that we observed. So again, going back to the deer, if you had, say, 20 deer and 40 rabbits, you could compare the relative densities of deer and rabbits by combining the number of individuals. In our plot sampling, frequency. So frequency being the chance that you're going to find a group within your sample. So if you have a number of quadrats that you've gone and collected information, how often are those individuals going to show up in any particular sample? And relative frequency is basically taking this relative density and turning it into a frequency. So being able to compare, well, if I saw lots of rabbits and not so many deer, what's the relative frequency, the relative chance that I'm going to encounter a plot that has a deer versus a rabbit? And then coverage is just the proportion of a plot that's occupied. This is something you more often use for something like a vegetation survey. So say you go out and you put your plot down in a grassland, you could say what proportion of the quadrat was actually covered by the plant of interest. So keep all these thoughts in your head, because these are the things that you're going to be asked to apply in half an hour on Long Gray Creek. Okay, transect sampling. Between plot sampling and transect sampling, you've pretty much covered almost all of field methods. Almost everything on some level involves either a plot or a transect. There's some other techniques that the next one I'll talk about, but really we're always trying to identify some metric and relating it often to an area or to an index. So the simplest definition of a transect is just a linear sampling method, and transects are particularly great in systematically distributing your sampling. So just you randomly lay out a line, and then you could select locations on that line in which you were going to sample. Or, and this is something that's really great in transition zones, so say you want to be looking at something in the intertidal or the subtidal through the beach, you can lay out your transect along a gradient and look for change along that gradient in the particular components of interest. And so you have to think about, well, how am I laying out my transect? Why am I laying out my transect? Where is it going to go? And what is it going to answer? So we're going to do some transect sampling in Cam Park, where we're looking at invertebrate density. And there's a river, kind of a river, Cayugas Creek, that is on one edge of Cam Park. And thinking about, well, if we oriented a transect perpendicular to the creek, or if we oriented a transect parallel to the creek, are we going to get different pieces of information from that? Okay. So here's another great example of combining methods. So these guys have a transect running through the intertidal, and they have quadrats that they're then going to sample some particular component of interest within or along that transect. So there's really three big types of transects. We've got the line intercept, and so a line intercept, taken to its most simple, is you basically stretch a tape or a line or whatever, and you only are counting things that cross the line. So if you stretched a tape out and you found plants right along the line, you'd only record the ones that are right on your line, not, a little bit off the line. The challenge with a line intercept transect is it's going to result in an index rather than some sort of absolute aerial estimate. And so that was the question that I'd had with you earlier on our deer road idea. We're kind of doing a line intercept transect there, where we're seeing deer just along the side of the road, or a roadkill survey could be another sort of line intercept transect. It's not going to tell you necessarily the density of animals in your area, but it's going to give you a good index. And as long as you have some sort of length or time or whatever combined into it, it's going to give you an index, but not the absolute density of critters. A strip census or a line transect is one you'll read about it in. I can't remember what the paper is. I think it's Keeping in Pelletier, where you basically have a linear transect, and then you identify a distance off of a line, and you can come up with, there's some math that allows you to calculate densities off of that. It often results in indices, but you can use it for density. A belt transect, it's only kind of a transect. It's kind of actually more of just a long and skinny quadrat or plot. It's just basically a very long, skinny rectangle. And again, transects are often combined with other methods, including quadrats. Let's see here. So some of the parameters you might get out of a line intercept are the intercept length. So say you stretched a tape across a creek and you wanted to say, well, how much of it is covered in willow? You could do a line intercept transect that said, okay, from meter 1 to meter 10 is willow. It's bare ground for meter 10 to 15, and then it's willow again for these other segments. You could also get a linear density, so you could count the total number of individuals divided by your total length of transect. Okay. All right, so let's go to one that's a little bit more complicated. And I will admit that point quarter sampling is something that I have never had to employ in the field. This is very much oriented more towards the vegetation surveys than it is to aquatic systems, but partially because aquatic systems are sort of a linear system. But I will give you an example of a USGS protocol that uses point quarter sampling in the context of a riparian area. So this is often called quadrant sampling, not to be confused with quadrat sampling, and it's basically quadrants of a compass. And the one challenge to point quarter sampling is it's sensitive to deviations from our random distribution. So it's not super great if, from the first slide in this presentation where we had, the plants lined up in evenly spaced rows. It doesn't work super well for that sort of context, and maybe remember that when you're taking your reading quiz. It also doesn't work very well if things are really clumped, because you might not actually encounter, it's usually you're going to end up underestimating or overestimating the abundance of the thing you're interested in.
Don't we want to have regular distribution?
You'd want to have a random distribution.
Random distribution, right? Okay, sorry.
So if it's really regular, then some of these things are gonna, I think overestimates in regular and underestimates in clumped. But you have to go back to the book on that. But the basic idea of point quarter sampling is you have a starting point. You divide it with your compass into quadrants. So you have 4 quadrants. And then within each of the 4 quadrants that you identify, you take a measurement to the nearest thing of interest. So it's the tree, you take the measurement from here to here, and then in this quadrant, you take the measurement from here to here, and so on. And that does allow you, with some math, to calculate an aerial estimate. And so here's an example of combining it with a transect. So USGS has a protocol of measuring habitat quality, and so they have some information that they're gathering on a transect through the stream, and then at the end of their transect, they pull it onto the bank, and then they do quadrant sampling and estimate riparian vegetation in there. So again, an instance where you can combine different methods depending on what you're trying to do. Okay. Does anybody have any questions on those? Because those are all like super fundamental, and I want to make sure you really have them. Yeah.
Do you post the slides?
I am not going to post the slides, but I'm going to post the recorded video. So you can rewatch the lecture until you hate hearing my voice. Okay. So sample timing. So I know this is probably obvious to you, but particularly when you're thinking of maybe doing a capstone project, and your capstone project maybe has some time restrictions on it, and you're only probably going to collect data during a particular time of year, you might want to think about what does that mean for the thing that you're interested in. Is it going to answer the question you're interested in? And so I have this cheesy picture of a single plant over the course of the year, and depending on when you sampled, say maybe you're going to come and you're going to measure leaf density, and that was something you're interested in, or maybe you're interested in insect density as related to leaf density. Well, depending on when you come, you may get a very different answer, and those all may be interesting answers, but it may, if you collected from one area at this stage and one area at this stage, it's probably not comparable information. And so thinking about the frequency at which you sample, the timing, and the seasonality of what you're up to. And in some cases it may or may not matter, but in other cases it can matter a lot. Okay, so metadata. And I'm using this term metadata loosely. It's got sort of it's a technical definition, often in sort of the software world. But I'm using it to describe sort of the set of data that describes the information about other data. So basically, all the things you should absolutely be writing in your field notebook, maybe things you'd want to have in your data sheets, things like environmental conditions, maybe who was sampling it. So my personal experience is we do bullfrog hunting. Some people are really good at seeing bullfrogs, but maybe not so good at hunting the bullfrogs. Some people are really good at seeing and hunting them, and some people just are not good at either. And so thinking about who's involved may change how you calibrate their efforts. You may want to have some description of the methods you're using, or even if it's not on your same data sheet, you may want to have a place where somebody could go look, or you could go look most often. What method did I actually use to collect this piece of information? So again, you can't write down too much in your field notebook, but you have to balance it between getting your work done and writing things down. Sometimes it's good. One of the practices I like to have is, say, we go out and we do a project for the day, and I'm writing things down during the day, but at the end, I sit down and I think about what are the things that we did today that maybe are different from another day. Sometimes I just write down what time did we leave, because that's really important for next year when I'm trying to plan, okay, we're going to go and do bullfrog hunting. Well, sunset was at a different time. Did we have enough time to do the tasks we needed to do before it was sunset? So those sorts of pieces of information can be very helpful. Okay. So that was our speedy introduction to field methods. And now I want to give you the opportunity to be creative and think of how you would address an environmental problem, an environmental issue. So Long Grade Creek does everybody know where Long Grade Creek is? You probably all walked over it on your way here. So we're just right over here, and Long Grade Creek, where am I? Yep, there it is. Goes along the edge of campus. And there were 2 construction projects that happened within the last couple of years. And I want to show you some Google Earth imagery over that time and talk about some of the restoration. And Sean Anderson put together a couple videos talking about some of the results that they'd seen of their restoration project here. So I'm going to have to switch. All right. So I assume probably all of you know that you can look at historical imagery on Google Earth. I want to initially say Google Earth. So how many of you guys have done GIS so far? Okay. So Google Earth is good for some things. It is not a GIS program. It's not really meant to be a GIS program, and it's missing some of the major components, like being able to query your data, being able to combine different pieces of information. But for quick and dirty, it's really helpful, and it has all this historical imagery built into it. So we're going to look at some historical imagery. And okay. So these are the 2 bridges. The little footbridge that goes over the parking lot, and then this new road bridge. And I'm going to challenge you to try and collect some information that would allow you to answer the question, has this restoration project been successful? Have we been able to restore Long Grade Creek? And I want you to think about it, and think about it sort of really broadly about how would you qualify whether something is a success? This is say again?
You need a baseline.
That's one thing to think about. So it's one of the biggest challenges in restoration and conservation is what are you comparing something to? And so I want you to think about that when you're doing this and whether the information you're collecting would help you answer that. So let's look back. All right. Okay, so this is Long Gray Creek in June 2009. You've got a couple of components there, it's a little blurry. You've got a couple of components that are, I think, very interesting. One, the spacing of these levees, the distribution of the vegetation, okay, so this is April 2011. You can see big construction project, some of the levees are getting moved, basically bare ground in these areas. Now we're to December 2013. You can see the levees have been moved back a little bit. You can see still bare ground in these areas around the construction project. And again, you can see again how clearly there's not much vegetation there. And now we can see some of the vegetation coming back. So what you guys are challenged with is to go and try and assess this restoration project. I have a couple of tools for you to do it. Emily has put together some transit tapes, some quadrats, some yardsticks, and some clipboards. I have some vegetation guides for you.
Cool.
So we're going to split into, I think there's only 9 people, right? So we're going to split into 3 groups of 3. And you can come and grab a vegetation guide.